called Google. She's the best engineer in oil painters and oil painter in engineering. So give it up for Aysylu Greenberg.
Dobry den. I grew up in Russia, so I speak broken Serbian. I'd really try to get by with my Russian here. So, welcome. If you're eating lunch, please feel free to continue enjoying your lunch. I'm a loudspeaker, so I'll be able to talk over the sound of the metal forks and everything. And let's talk about zero downtime migrations. This is not an old painting I did, but it's a drawing I did to portray what I felt like when I led the zero downtime migration at Google for distributed build system, which is the examples that we'll primarily use today to discuss how to do this successfully. It kind of felt like trying to replace the jet engine of the flying airplane in place with no downtime. The plane just continues going, and that was a hard challenge. So let's talk about what allowed us to be successful in this. I'm Aysylu Greenberg. I work at Google. I've worked on a variety of infrastructure projects, such as search infrastructure, develop infrastructure, where I build the distributed build system, which I'll talk about today. And now I work on the Google Drive's infrastructure, making your Google Drive better. So, and I am online on Twitter. If you want to ask any questions, feel free. So let's talk about zero downtime migrations. And before we jump in, let's first define what migration means and what zero downtime means. First of all, how many of you have done a migration or multiple? Okay, I see lots of hands. How many of you are currently doing a migration? Okay, a couple hands. Okay, cool. Sounds good. So what is a migration? So there are many different types of migrations, and they can roughly be split into two categories: data migrations and architectural migrations. So for data migrations, what we'll have is we'll have an old storage system and a new storage system. And then we'll want to copy the data from one system to the other. And then when we want to confirm that the system behaves correctly and it gives the same results from the old storage system and the new one, so we'll write some sort of parity verification that allows us to confirm that the migration is going successfully. And then we'll start serving the results from the new storage system. For architectural migration, the simplest example is probably the pattern that we've used so far, which is client-server architecture. And now with the migration to microservices, many different companies and teams realize that's a good idea for them. It might not be a good idea for every project, but we have a lot of microservices-based architecture. And so in this case, the client will send a request to one service, which will send another request to other services, and the client will retrieve information from yet another service. So this is roughly what the shape of the migration is. And every single migration will look differently for you. It will have different steps associated with it, but we are going to talk about similar patterns, common patterns that occur across all migrations. So now let's talk about zero downtime. And before we do, let's just make sure that we understand. So how many of you see the notification maybe by your bank or by another government agencies do that a lot, where they say the system will be done for 2 hours on Sunday, maybe nobody actually uses it that much then, so it's a good time to turn off the system, do some maintenance maybe, do the migration then, and then turn it back on. Yes, has everyone seen that? Yes, okay, so totally reasonable way of conducting your migrations, because the service is not actually needed. Users can tolerate some amount of downtime during that time, and so you don't really need to do zero downtime migrations. It makes it simpler to plan, it makes it easier to verify that things go successfully, and then when you turn it back on, either you turn on the old system if there were some issues, or you turn on the new system if everything went fine. So, however, when your system gets really, really big and you have lots of users expecting to be able to access it 24 hours, 7 days a week, then that luxury of downtime is not an option. And so for the rest of the talk, we'll talk about one of those systems, which is the distributed build system, where downtime was not an option for us. And so we needed to figure out how to migrate with no user visible effects and to be able to do that successfully and with no outages whatsoever. So let's talk about the build system, which is the main example I use today, which is the project I've worked on and led the migration for a part of it. How many of you use Maven, Gradle, Rake? Okay, so this is the type of build system that we're going to talk about, and each language has its own build systems usually. So usually we start out with a single server build system, right, where we will type the command, Maven build, and then it will fetch the dependency for us from the cloud somewhere. It will know how to fetch them, and it will build them on our machine. So now as the project gets bigger and more popular, there will be a team assigned to it, at which point the team will set aside a machine, and they will try to do the same operations and test their system and deploy it. So now as the company grows bigger, there will be each team will have to do this thing where they set aside on the side a box, and then they use this. And so this challenge here is that each team needs to understand and spend some amount of energy and time understanding what went wrong with the build system, how to upgrade their box to be able to do the latest, use the latest features. And so what this means is every single team now has this overhead of doing this. And this is fine, but if the team is, for instance, machine learning specialists, or the team is back-end engineers, they might not necessarily all of them have expertise in build systems, so everybody will have to dedicate some time learning about it and learning how to operate it. And that's where the team like mine, the build system team, steps in, where now, instead of having each team to do this part of work, we'll create a shared infrastructure. So now the team, my team will basically operate all of these machines, and now each team can send their requests to the build system, and they can get advantage of having all the testing and the deployment done for them, but they don't have to worry about it. And we can also, because we know about certain popular artifacts that are being downloaded, for instance, like TensorFlow in a machine learning company, then we can do something about the caching of it. We can do something about ensuring that users get their builds quicker done, because we know that certain dependencies can be used very quickly. We'll make them available as soon as possible. And if any of you use Travis CI or Circle CI, I see a couple of hands. So that's, it's similar to what this build system does, but out in the open outside of Google. Okay, so now, so the system, the distributed build system, is called BuildRabbit, and so we looked at how it develops to this stage when the companies actually have the business need to develop these systems. So let's look at where it sits and why the luxury of downtime is not an option. So BuildRabbit sits very nicely in the middle of the build and test stack. So there's multiple applications that rely on it, such as continuous integration system and our release infrastructure that actually deploys it. It will code to it, build the artifacts, and then have those artifacts deployed out. Individual Google engineers and teams will use the system. And also, the integration testing infrastructure will send the build. It will build all the dependencies, then bring up the environment in a separate sandbox, and then verify that integration tests are passed. Now, BuildRabbit system itself relies on a few components, such as the source system. It needs to know at which point in time which revisions should be applied. So for all the commits that you have locally, what the source code looks like, what the code base looks like. And then it will build it based on that, and then send the notification to Blaze, which is the internal single desktop build system that you can think about it. And then this system will send the artifacts somewhere to store them, and then BuildRabbit will know how to retrieve them from there. And if you were in Casey's talk, you heard probably about Bezo, which was open source a couple of years ago. So if you're interested in trying it out, this is what we use internally as well. And it's great from my own experience. So now let's talk about the architectural upgrades. So those of you who are from Royal Grade will recognize this is the Kalimekdan fortress. It's really, really cool. I just went to visit there yesterday. And so this fortress, served for many, many centuries to protect the city, and it worked really, really well. The problem with that is that in modern day, when we need to build high urban density buildings, it is very expensive to build that. So there's no problem with the specific architecture that was used. It's just that it's not possible to scale it to many more people that need to have a place to live and execute their business. And so we need to figure out a new architecture to build. And that's the problem that BuildRabbit started running into, where the architecture that we used previously worked really well for a long time. And then at some point, it was become so popular and became used by everybody in the company that we needed to be able to scale it and scale it for growth as well. So that's when the need came. So the old system was old architecture was pretty simple. It was, client server with some load balancer. So the client would send the requests to the BuildRabbit scheduler, which will basically tell it which worker machine to talk to. So it operated as a load balancer for the client. And now, once it knows which worker to talk to, it would send the request to the worker, and then the worker will send all of its responses, all of the information about the build progress back to the client. So this worked, as I mentioned, really well for many years, but there were a couple issues that we started running into. One of them is the client library needed to be a very thick client library because it needed to know how to do the routing from the scheduler, the machine that it told it to talk to the worker. It needed to understand all the error codes that was sent back by the scheduler and the worker to figure out if it was a transient issue or permanent issue and figure out where to retry the build or just wait for the machine to fix itself. And also, you see how it only has one connection to the worker? So if that connection got interrupted, that means all of the build progress was lost, which was a big problem for big builds that take a pretty long time, because that means you had to retry again somewhere else. And so we needed to figure out a better architecture to do this. And so we ended up coming up with a build service system, where now client sent the build request to the persistent queue, which saved that. And then from then on, when a worker had some capacity available to it, it would dequeue it from the queue. And then it created two types of outputs. It created build progress information, for instance, which tests have passed and how far you are, how many source files have you already built and linked, and so on. And it also produced artifacts, which would be used as binaries to deploy later. And so now it would output those, and then the user had the option of figuring out, does it want those binaries to be deployed afterwards, in which case it could choose that, or it could choose to have the build progress information, at which point it would know that you needed to know how many tests have succeeded so far, maybe exit early and retry after you fixed the test bug. And so putting it side by side, so these boxes make up the build service here. And putting it side by side, what we had is a client library with a server and a load balancer, the scheduler, and then we had many more boxes. So now this architecture may look a lot more complicated, and it is. As it happens with microservices, the more boxes you have, the more things you need to understand about how your system behaves. But it allowed us to do one very important thing. It allowed us to move the resilience logic from the thick client library to our service itself that we own. The reason for that, and the reason it's so important, is that when you have a thick client library that you give to the users, the point of creating a shared infrastructure is you don't want your user to have to rebuild their client over and over again as you come up with bug fixes, right? Because what's the point of having shared infrastructure if you have to bother them every week or every time you have a bug fix that they have to rebuild it? So what that made it more difficult is rolling out these feature requests, and then we needed to figure out what is the cutoff point at which point we don't support the broken versions of it. With the new architecture, it allowed us to roll out new features a lot quicker to our users, and the client library is now a lot thinner. It needs to do a lot less of understanding of what happened on the build system, and then all of us on the build system could figure out best improvements that we could make for the client and roll it out as quickly as possible. So, as I mentioned, the BuildRabbit system sits very nicely in the middle of the stack. And so a lot of the requests that are coming in from the left-hand side of this slide a lot of them are automated. So you expect 24/7 being able to access them. And so downtime, it was just not something that we could afford. We couldn't just ask our users to stop building and testing because everybody had their own rollout mechanism, and we couldn't just ask them to stop doing that. And so for the rest of the talk, we'll talk about how to execute migration with zero downtime. We'll talk about both architectural and touch on data migrations. I've been involved with several migrations at this point, and I've led a couple. And so this is going to be, common lessons and considerations to know about as you're planning your zero downtime migrations and things to look out for. Every migration is going to look different for you depending on your previous architecture, depending on your considerations. So this will cover majority of the common considerations in order to make sure that your migration is successful. So who's familiar with this person, Novak Djokovic? Yes, great tennis player. So I don't know too much about tennis, so my analogy might not make sense to the tennis aficionados, but basically the idea here is we want to focus on the intermediate state. So by the time the ball lands in the racket, like that's it, we made the contact, and the way we send it is pretty much has been described to us. So it is before it hits the racket, it's while it's in this intermediate state is when we can make most of the decisions and anticipate different failure modes and react to them is when we would like to do this. And so one of the important things to remember is focusing on intermediate state. One of the reasons for that is also because we know our old architecture very well, because we've been operating the system, we've been working on it for a long time. The new architecture is also something we've spent a lot of time designing and discussing and making sure it's the best way forward. However, getting from old state to the new state is the least well understood as we start our migration. So it's very important as you start on it, as you start thinking about migration, to focus most on that. So prepare to write a lot of code for the intermediate state. It might be throwaway code that you, as soon as you're done with migration, you just toss out. It might be code that you keep around for a while because maybe your migration takes a long time, or you intend to keep old pieces in place as well. So for the build system migration, I specifically led the moving the worker from talking to the client directly to dequeuing it from the queue. And so let's look at what the intermediate stages look like. So old stage was client talks to the scheduler, then it gets response back for which worker to talk to, and then it gets the results from the worker. Now the new state is we have a persistent queue. So the client will start sending the request to the persistent queue, and now it will stop sending the request to the old build rabbit worker. And at this point, build rabbit worker will finish up the in-flight request that it has, and as soon as it's done with those, it will start dequeuing it from the persistent queue to use the new architecture. And now the client will stop receiving information from the worker directly, or the outputs directly. And so at this point, we arrive at this stage where worker doesn't talk to the client directly, but instead it talks to the persistent queue, and then we pass the information. It's not pictured here, but we have other ways of providing the output, as I showed the two extra boxes in the service. So understanding this code paths was really, really important to make sure we get the order correct, so that we don't mess it up and that it doesn't affect the user at all. And from the perspective of the user, it still behaves the same. They send the request, and then they get the response back. So now it's important to also know that the quality of the software you write for the intermediate states should be proportional to the lifetime you expect. So if you expect that the migration will take, say, a couple months, couple weeks maybe, then you could just write code, not worry about it, make sure you spend more time on other pieces of the migration, but generally not worry about having the highest quality of code. However, if your migration is expected to take a long time, or you intend to keep some old pieces around for a long time, then it's worth investing some energy into ensuring that the quality of code you write is great. And so in this example, for instance, with data migration, so the intermediate stages that we have to worry about are copying the data from old storage to new storage, and then doing the parity verification, comparing the results returned by the old storage and the results returned by the new storage. Do they look the same to the user? And at this point, you might decide that maybe copying of the data at some point will end quickly, but then parity verification, maybe you'll keep that around because you want to really make sure that both systems behave correctly and really fix issues. Maybe you'll keep the old storage system completely together because it's too expensive to migrate to the new storage system completely. And so you'll keep both of them. Or maybe some of your users are just using really old version of the client, and you just have no intention of actually having them migrate to the new. So another important consideration is to focus on migrating backends first. The whole reason you might have started a migration is to be able to scale it better to your new use cases and to improve architecture for the actual use cases that your clients are requesting. And so at this point, it's important to prove that your backends work first before you make any changes to the client. So in this example, all of these are the backends. And so we wanted to first build them out before we start thinning out the client library. And we wanted to prove that it actually is able to scale to the current use and is able to support the growth before we make any changes to the client. Now, for the example with the data migration you might do is first you will ensure that the server that you build is serving from old and new storage. And then only then, once you've proven that at that layer the data looks the same that you would be passing back to the client, then you will start making changes to the client. So first you'll focus on anything that talks to the data storage systems to ensure that that system is migrated. You wrote the additional code to have the server serve from the new data storage. And it's also important to remember to invest time and energy into having visibility into your system. Once you start deploying your new system and you start migrating, can you actually tell what's going wrong if something were to go wrong? So there's a good balance to strike between spending a lot of time on monitoring and correct logging and metrics, which on its own could take quite a bit of time to do correctly. And so it's important to figure out what is sufficient amount. Maybe you throw some extra logs, but for now, you might have only some simple monitoring metrics to be able to see if something is really going wrong. And maybe as long as you know that if something goes wrong, you're able to actually see through what happens in the new system or the old system or the interaction of the two, then that should be sufficient. But it's really important to ensure that you have some visibility into what's going on. So for the intermediate state, the three main takeaways are make sure that you are prepared to write a lot of intermediate state code, whether it's throwaway code or the code that is going to stay around there, and plan for the quality of it to be consistent with how long you intend to keep it around. And you might have to come back to it if you realize that you have to keep it around for longer to maybe come back to it and improve it somewhat and then move past it. And make sure to migrate backends first, because that's what allows you to prove that the new architecture is actually able to scale to the extent that you think it is, before you make any changes to the client, any visible changes to the user. And finally, make sure to invest energy into having good visibility into the system, so that if anything goes wrong, you're able to detect why, and then be able to see the whole story instead of wondering what might have happened and not having full understanding of what's going on. So now let's talk about incremental rollouts. When you do these migrations, generally, especially with zero downtime migrations, you want to make sure that you roll out very slowly, gradually to our users. So a common example might be if you have 2 clusters in which your system is running, then you'll start rolling out one by one and compare at each stage. Every new machine, maybe you'll compare it to the old state and see if performance has degraded, maybe the responses started getting corrupted, or maybe you're no longer able to scale. And so slowly, as you roll it out gradually, you're able to detect these issues earlier and then react to them, fix the issues, and then continue with that. So now it's important to also ensure that you validate scalability with least amount of user impact possible. So in the example of data migration, so you'll have your old storage system, and you're copying the data as you go through, and now the client sends the request to the server. And most of the requests should go to the old storage system first, so the server will send it to the old storage system. And only maybe a small fraction of users will be impacted by the new storage system. So at that point, it's a lot easier to fix it for the few users instead of trying to fix it for all of them and creating a lot of confusion and frustration on the client's part. Now, also, it's important to remember to decouple launch of services if possible. In our case, our migration was very complex, and we wanted to ensure that it goes smoothly. And so we needed to find clients that are friendly to the launches. And so this allowed us to decouple them. And as it turned out, there were different users that were friendly to different types of migration, to different types of components being rolled out. The launch that I led was with the persistent queue and the workers dequeuing off of the queue. And for that, it ended up being that the client that we used really needed this functionality as soon as possible, so they were willing to work with us closely to ensure that the migration goes smoothly. For other components, other clients were able to benefit earlier on. And so we actually had separate set of clients that were affected by different types of migrations, and we did them separately. The other advantage here is every single one of these components hit some sort of roadblocks during this migration. And so by not having the whole migration depend on all of the components being ready at once, it allowed us to make forward progress and start improving our system and rolling it out, the improved system to our users as soon as possible without having to wait on all the components being ready. And that also required additional understanding of the intermediate states, what it means for one of those new components being up and both of them being up and then all of them being up. So the two main takeaways for rolling out gradually is make sure that you validate scalability of your system. The reason you start out usually is because you want to make sure that the new system is able to serve the demands of the users and is able to support the growth. And also decouple the services and make sure you can find, if possible, launch-friendly clients. So now let's talk about practicing rollouts. So I think this is the dancers doing a colo dance. And so just like they wouldn't get on stage without practicing first, even if they're amazing dancers, same with migrations, especially zero downtime migrations, you wouldn't do that without actually practicing the migration first. And that was one of the most important lessons I think that we learned during the migration is that how helpful it was for us. So one thing that is not obvious, perhaps, or is less obvious, is having a solid rollback plan. So if things go wrong as you start rolling out and you notice it, you want to go back to the previous state so the user can still continue using it. And so understanding how that looks like and practicing that was really, really important and beneficial for us for success. So in this case, so we had our client sending the request to the persistent queue, and then the worker was dequeuing it in the new architecture. And let's say we find some bug. And so what we needed to do is understand what the path to reverse it back looks like, and often it's non-trivial. And so in this case, it meant the user stops sending it to the persistent queue, starts sending it to the old path to the scheduler. Then it gets the result back, and then the worker stops dequeuing it off of the persistent queue. Now it will be in the new mode. And now it will start sending the request to the worker and start getting the results back. So understanding this sequence of actions and practicing them with all of us was really, really important. We were distributed across 3 different geographic zones, so it was like 3 different time zones. And so and there was like 5 different teams involved with this rollout. And so ensuring that everybody understands what the correct path is to ensure that there's no user visible impact was really, really important for us. And in the case of data migrations, you might find that, say something becomes corrupted, so you stop serving the request from the new storage system, and if there's not that much data to begin with, maybe you just scrap it altogether, and then you say, okay, I'll try again, and then you start trying the migration again. Maybe you'll fix the corruptions because you've spent some time understanding how it could get corrupted, and in which case you won't have to scrap your database and start from scratch. But understanding what the rollback looks like if something goes wrong that we didn't anticipate is really important. And also, something that came in really handy is using checklists. So what we had is multiple steps. I think it was maybe at least 12 steps in the rollout plan that we wrote, and ensuring that we understand we're on the same page about how the migration is going to go and how the rollback is going to go if at any stage we detect issues. There is a book by Atul Gawande, who's a neurosurgeon in the US who turned author. And so he wrote about the value of checklists for medical professions. If you're a surgeon, it's very important for you to have this checklist because smart people make mistakes, and it usually happens when they're really tired. So as we've been planning this migration, we felt like we understood it best at that time, but we also were the ones where we could miss just the simplest of the things. So checklists allowed us to make sure we don't make the simplest of mistakes that we obviously know how not to make, but we might have forgotten. And so I highly recommend sticking to this. It also allowed us to plan for organizational resilience. If somebody is on vacation or becomes sick, it was really easy for anyone else to step in and pick it up. So in order to ensure the success of migration, make sure to also practice the rollout. Have a solid rollback plan, and ensure you have checklists just so that the whole team is on the same page, and anybody could step in if the main leaders, the people who have been involved most for the migration for some reason, can't help out at that point in time when we need to keep the migration going. So there are three main takeaways to enable successful zero downtime migration are: focus on the intermediate state. Make sure you understand it really well as you start on the migration. Make sure you understand how the old and the new system will be interacting, all the intermediate steps, and how it would affect the user. And make sure that the user visible impact is minimal. Roll it out incrementally to affect as few users as possible and to be able to catch mistakes early. And make sure to practice your rollout. As we practiced it many times, we found issues with every single step in the migration. And we were able to build confidence by practicing it. And after we did it a few times successfully, we were like, OK, I think we're good to go. So this really allowed us to roll it out with no downtime for the user and no users were affected negatively. They only got all the improved parts. So this is all I have on zero downtime migration. Hvala vam. And I'll be happy to take questions. OK. Well, if anybody wants to just raise your hands, and I'll be happy to try to answer the questions.
Questions? Concerns? Comments?
Questions? Is everybody hungry and ready to eat?
Yeah,
yes.
Question?
Go ahead.
Hi, which tools do you use for monitoring your systems, your internal systems?
Mm-hmm. So the tools are all, unfortunately, internal. So the names of it wouldn't be helpful. But the gist of it is, I can tell you a little bit like the internal architecture, if that's helpful. We don't use any of the open source tools that you might know about. So the gist of it is we'll have a library that basically knows how to send the metrics over. And then we have a service that collects those metrics. And then we have a different service that basically knows how to render the time series. So it will store them in a time series database. And then it knows how to aggregate them and do different statistical interpretations of it, and then monitor them. None of them are open source, unfortunately, so I won't be able to share useful information about the good tools out there, but the general approach is this.
OK, more questions? No? OK, you can ask questions afterwards as well.
Yes, so I'll be around. I'll be getting lunch after, so if you want to join me and ask more questions as you think of them. Thanks for your attention.
Thank you.